Hey folks, welcome to this channel and welcome to this video. I'm Saptarshi. I'm a software engineer 3 at Google and a competitive programmer. So in this video, I'm going to discuss a very interesting problem, Book Shop, which is based on the one of the most important parts of DP, the Knapsack DP. So let's see what this problem is and let us understand the Knapsack problem. So the problem says that in a bookshop there are n different books. We know the price and the number of pages for each book. So for each book, we have these two information, number of pages and the price. Now we have decided that the total price of our purchases will be at most X, maximum X. What is the maximum number of pages you can buy? So the price has been bounded. We cannot cross the price. And the number of pages we have to maximize. What is the maximum possible number of pages we can buy? You can buy each book at most once. So each book can be bought at most once, and you cannot tear a book and take half of its pages. You can't do all those things. Right, so this is a particular case of a knapsack. Why a knapsack? Um, because it's basically you have to take some items, keeping a particular parameter under control and expanding the other parameter. So let us see. The input, we have some books and some maximum total price. This is your bound on the total price. And then you have the prices of each book and the number of pages of each book. You have some input given. There are around 1000 books. The price goes up to 10 to the power 5, and the number of pages or prices of each book, they go up to 1000. Now let us understand. This is knapsack problem where we are basically saying we have some n items and we have some knapsack or container which has a capacity of bearing up to X price. That is, your price has to be lesser than equal to X. Sometimes instead of price you have weight, that the weight of the items, total weight, has to be less than equal to something. Here the price has to be less than equal to something, and the price of each item is given. So one item will have some price and some pages. So price and pages, PR1, PG1. You can have PR2, PG2. Similarly, you can have PR3, PG3. You have to choose some items such that their sum of prices is less than equal to X and their sum of pages is maximized. So basically, if I say I will choose this one and this one, that means I need to ensure that my PR1 plus PR3 is less than equal to X. This is my constraint, and it would mean that my total number of pages would become PG1 plus PG3, and I have to basically maximize it. So whichever combination of two elements, three elements, one element, whichever combination gives me the best number of pages, total number of pages, with the price under control, I will go with that. So it's similar to basically saying that, hey, I have this much budget and now I have to purchase some items. Each item I can purchase at most once. Now can you tell me which items to purchase so that my number of pages or some happiness factor is basically increased. Here happiness factor is basically number of pages. So which books to select so that the happiness factor, that is the total number of pages, is the maximum. Now a basic idea is, why not choose those items which have largest number of pages? Sometimes it may go wrong. For example, let's say you have X equals to 10 and you have some items like the prices, let's say prices and pages. It may happen that some item, some book will have a good number of pages, something like 11. So for some price you will have, let's say the price is 10 only, but there are some other things like you have 5 and 4. For price 5 you might have something like 6 pages. For 4 you might have something like 5 pages, or let's say again 6 pages. So somehow you cannot take all of them, but you can choose to take these last two. This will give you 12. This will give you only 11. So if you choose the 11 one before, that hey, this has the maximum number of pages, let's choose that one greedily, that will give you a wrong answer. You should not choose anything greedily. Similarly, there is another approach that hey, I will find out the number of pages per unit price. So you'll find out this ratio. This is also a greedy algorithm which does not always work. Like we can create a case. If you follow this particular thing like over here, you can say okay, this is 10 by 11, this is sorry, pages by price, so this is 11 by 10, which is 1.1. Here the pages by price ratio will be 6 by 5, which is 1.2. Here it is 6 by 4, which is 1.33, I think. 3 by 2, sorry, 1.5. 1.5. So we can say the maximum one we can pick up first. So we will pick up this one first, and then we will pick up the next one, which is this one. So we will get the best answer in this case, but for some other example, we can get a bad answer. So you can imagine this kind of a case that we have 10, 11, and then we have something like for 6, I have 8, for 5, I have 7. Now if you find out the ratio, I think 11 by 10 will give you 1.1, 8 by 6 is 4 by 3, which is 1.33, and 7 by 5 is something like 1.4. So somewhere the last two are winning. We will say this won, so take this one first. If this one comes, now I cannot take any of the others. This is a bad choice. So somewhere the greedy algorithms are not working. What algorithm will work? One algorithm that will work is take any combination, like take all possible combinations and see which combination works. So you can try out all 2 to the power n combinations. If there are n items, you can try 2 to the power n combinations. This is exponential in the number of items. N is 1000 over here. So if you try 2 to the power n combinations, then basically select an item or not select an item. There are 2 options for each item. Thus you get total 2 to the power 9 combinations, 2 to the power n combinations of which ones to pick, which ones not to pick. So basically if you go that route, 2 to the power 1000 is beyond your control. You can't finish within the time limit. So we can't solve in this way. 2 to the power n combinations is not going to be a way forward. How to optimize? Now we came very close. This is sort of a precursor to a very close approximation algorithm, but we will not go in that direction because those are slightly different areas. We will come to our approach of dynamic programming through which we can solve this problem. What we saw till now is we have to take some items, we have to maximize something while keeping the other parameter under control. This is something true about all these knapsack problems. So knapsack, you basically have to choose items where there will be multiple parameters, maximize one parameter, or you may have more than one parameter to maximize. Some expression you might have to maximize based on 2 parameters. Maximize one parameter and keep the other parameter or parameters within bound. Keep the other parameter within bound. So this is that category of problem where DP is very famous a technique. Let us look at the technique. So what we do is we say, hey, you have, let's take this example, it's given in the problem. You have 4 items. These are the prices, and 5, 12, 8, 1 are the number of pages. Now what we will say is that if you get 4 books together, it becomes difficult to decide that which one to take, which one not to take. So take one book at a time. Take one book and say, okay, if I take up to this book, so sort of something like this, if I take up to the first book, for these different cost thresholds, what is the maximum number of pages I can gain? Up to here, what is the maximum number of pages I can gain? Why am I saying this? I basically want to look at it in this way that, hey, with x equal to 20, with x equal to 20, If I take this particular item 5, 8, if I take this particular item, that means I am saying that I am leaving 20 minus 5, that is 15 for remaining books. If I take that item, that means I'm leaving 15 for remaining books. If I take the previous item like 8, 12, okay, I took x equal to 20, maybe I can take x equal to 10. If I take x equal to 10, that means I'm leaving 10 minus 5, that is 5 for remaining books. If I take 3, if I take 3, 1, this particular element, that means from x, I'm basically saying, hey, I'm leaving 10 minus 3, that is 7. 7 price available for buying any remaining books. 7 for remaining books. So understand this, that I'm basically saying if I pick one element, then for that element I'm taking the decision. For the other elements I am leaving the decision to be taken for a shorter price, for a smaller price. So you can understand there are two parameters. One parameter is this price. So the moment I'm taking an element, I have to look at what happens in a smaller price with a different subset of elements. Can they take something and give me the highest bucket, largest bucket, something like that. So somewhere these being the states is logical. The way we have been having for previous problems, that our price is one of the states. For price 10, for price 5, for price 3, for price 7, what is the value that I hold? What is the total number of pages, maximum number of pages that I can hold, or that I can accommodate? So yeah, 7 for remaining books, 15 for remaining books, depending on this. So let us fill this table, let us understand what it means. First step is, let's say you don't take anything. I'll name these items as A, B, C, and D. First step is, if I don't take anything, then what is the number of pages? I'm deciding what items I'll pick. Then I will decide if I can take that or not based on these, the available prices, and then I'll fill in whatever is the maximum number of pages. So the above table will contain the number of pages. We will come to that. Let's say I'm not taking anything, then my number of pages basically is 0. If I'm not taking any book, number of pages is 0. Now let's say I'm taking the first element A, whose price is 4 and number of pages is 5. Then I can say that the price is 4, that means before 4 I cannot take this element. Before 4, up to 3 I cannot take this element. So yes, you have given me A, I'm basically taking A. I can choose A, but in these cases I cannot choose, so I will sort of surrender. I will say whatever is there without A, I will have the same values. 4 onwards we have a possibility. We will say for 4, we will say that hey, A has 4 price, so we can buy this with 4, and we can go back to 4 minus 4, 0, to see with that price what did we take over there before we took A. Before we took A, we did not take anything, so it was 0. We will say okay, after this 0, we are basically taking this 5 pages, this particular book, so we have 5. We know that for any capacity greater than equal to 4, we can take the first book, so we will fill it up with 5. What does this 5 mean? This means that with this possibility, what is the maximum number of pages that you can get with only A being there, with only that book being there, not the other books, only that book being present? 5 is the maximum possibility. Now let's say we take another element just for flexibility, sort of We already have A possible, now we are bringing in B. So from A and B we can choose. So now the question is, if I have to choose, if I don't choose B, that means I'm basically referring to the previous row. Previous row has only A, I mean only A as the possibility. Now I'm saying have A or B as the possibility. That means either the previous row or some better answer if I take B. If I take B, then if I get a better answer, I will choose that. So somewhere, if I mark these rows in this way 0, 1, 2, 3, 4, then this table, I can say that dpij basically means the maximum number of pages possible with total price less than equal to j and using books only from 0 to I minus 1. According to the question, from 0 to I minus 1. So basically for 1, we are only going to consider the book 0. For I equal to 2, we are going to consider only the books 0 and 1, the first two books, and so on. Using those books, what is the maximum possible number of pages? This I doesn't mean that using I books. It means using the first I books. What is the number of pages present? That is the first I books. That is using the first I books. So let's fill it. Here, what strategy will come? This is the strategy that for the price J, either I take the ith option or I don't take it. Either I take the I minus 1th book or I don't take it. Let's say I take it. If I don't take it, then basically it will be dp of, I, I minus 1 J. That is the same price, but I will not take the current book. This is if I don't take the current book. And if I take the current book, that means I will get the prices, the pages of I minus 1 plus dp of I minus 1 using the other I minus 1 books and using price J minus prices of I minus 1. Why? Because I am taking the I minus 1th item. The minimum of these two I have to consider. The minimum of these two becomes, so this is if okay, so the second condition is valid only when this is greater than equal to 0. If this is not greater than equal to 0, don't consider this condition. If your J is less than prices I minus 1, then you cannot use that. So let us look at our recurrence relation. Using this recurrence relation, we will solve this. So this is the previous row, that is the top element, and this is the top left element. So let us look at it. When I have B has 12 pages, price 8. With price 8, it can only come at these places and with 12 pages. So for these I can say, hey, if I take the top one, I will get 5. If I take the current, this second book, which has price 8 and pages 12, then at price 8 I can basically get 12 by taking this. So I'll take the maximum of 12 and 5, which is 12. For these cases, I will get 12, 12, 12, and all the left cases I'll basically get whatever is there on top. 5, 5, 5, 5. Now I think we can have some fun. Let's see. Now we will consider the third element, C, which has price 5 and number of pages 8. Now we can say that 5 onwards is our possibility. Before 5, there is no possibility. You can just copy the above values. 0, 0, 0, 0, 5. Now here onwards our possibility is there. We can take from the left or from the top. So let me show you one example. Let's say this particular example, or let's say this particular example. 5, 8. That means I can take the top one only. I can totally discard this one. That is a possibility. So then I will take only the top one, or I will take this current element, which is 5, 8. Price 5 is going away, so I have to go 5 steps back and say 9 minus 5. 9 minus 5 is 4. So at 4, using 4 as the capacity, what is the maximum price you got? That plus my number of pages. What is the maximum number of pages you got? So that plus my number of pages 8 gives the value 13. So if you take this book, then basically you will have 8 pages and 5 prices gone. So you'll go back by 5 prices and you will say that 9 minus 5 gives me 4. So with price 4, what is the best that is possible? That we will read from the previous row. That okay, I've taken some part for my own item, then leaving that, what best is possible for that thing, for the previous items. So with 4, you basically see 5 is the best thing. So 5 plus this 8 gives us 13. So we get from the top left we get 5 plus 8, 13. From the top we get 12. So the maximum is what we take, that is 13. Sorry, it's not the minimum, it will be the maximum. We want to maximize. This is a maximization problem. I'm sorry. We will take the maximum. Now similarly, we basically treat it in the same way, 12 and 5 plus 8. So here also it's the 13. In this case, if you go back by 5 steps, when you have 8, if you say I will spend behind this one, 8 minus 5 is 3. From 3 you will get nothing. So if you go back by 5 steps, you will see the same thing. Going back 5 steps, you have nothing. 0. Means if you spend 5 pennies here, you won't have anything remaining for any other item. You have to stay pacified with this 8. So okay, in this case, we can say, for this case, follow what you are getting. From the top, you are getting 12. From the top left, you are getting only 0 plus 8, that is 8. So take the maximum one, that is 12. Similar here, we will get 5, 5, 5. Now the last step, we'll have one more element, A, B, C, D. Same strategy, 3, 1. When I say 3, 1, before 3, no use, basically copy whatever is there on top. Before 3, we will say, okay, we cannot take this item because we don't have sufficient price. We'll copy whatever is there above, that is these 3 values downwards. So 0, 0, 0, 0. Yeah. Now this 3 onwards. We can now do the same things. 3, we can take the current thing, that is 1, and then we can do 0 plus 1, 1, and from the top it is 0. So the maximum one is 1. In this case, the maximum will be 5, and so on for the next cases. Wait. Yeah. Minus 3. So here also it's 5. For this case, we will say, hey, it can give 1, and it can, there 3 will be consumed, 3 price will be consumed. So go back by 3 places, you get 5. So 5 plus 1, it will become 6. From the top, if you take, you will take 5. From the top left, you will get 5 plus 1, 6. So you will follow 5 plus 1, 6. Similar over there, 12 or 5 plus 1, 6. In that case, 12. Similarly, 13 or 1, 2, 3. 13 or 5 plus 1, 6. We will get 13. 13 or 5 plus 1, 6. we will get 13. So the answer turns out to be 13, it seems. Yes, 13. And you get you are buying the books 1 and 3. If you look at this, that's exactly what you're doing. This 13 comes by taking which one? Basically it comes over here, and over here it gets changed, like previous step it gets changed, which means you're definitely taking this last item C, due to which it has differed from here to here. So you're taking this 13, and now it has come from uh, 5 steps before, that is 1 2 3 4 5. So over here it is coming from here. If you look at this 5 is coming for the first time over here. So we are taking this item. So we are taking the first item and the third item. In that way we are reaching this optimal value of 13. That is the maximum number of pages you can gain. So very interesting algorithm. It's a very interesting strategy to solve these kind of problems where so many decisions have to be made. And you could do it in basically number of items multiplied by total price. So if your total price is under control, over here it's 10 to the power 5. Your number of books is 1000. So it total comes out to be 10 to the power 5 into 1000, that many cells. So if you count the number of cells, the space complexity is n into prices. So the prices, that is x, which is 10 to the power 8. Time complexity is also n into x, which also is 10 to the power 8. You can treat both of them as big O n into x. Now, from the space complexity perspective, you can see that this is a bit too much for space. It's really difficult to handle so much space. So is there a possibility to optimize this? Now we have discussed our 2D to 1D transition few videos back. That was a slightly more difficult problem than this one. Over here, if you have to reduce the states, here we went in a row-wise manner. Look at this. When you came to this row, did you need the previous 2 rows? When you came to the third row, did you need the first row? When you came to the third row, you just needed the previous row, right? According to this condition, you just need the previous row. The previous row's jth value, the previous row's some other value. You just need the previous row from any row. You don't need all the previous rows. So if you just need 2 rows at a time, the previous row and current row, and you keep on reusing that, then you can reduce the time. Instead of n into x, it will become just 2 into x. You will just deal with 2 rows at a time, not n rows. So just recycle 2 rows. So yes, that is a common strategy where we say that, hey, do something like this. This is another state reduction or space complexity reduction. Space complexity reduction in DP. So we can basically say we have 2 rows, zero, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we will say, okay, initially it's 0, 1. When you have 0, that means there is nothing, you have all zeros. And now you will start filling up from 1. 1 basically means your first element. So we usually start from 0, basically saying that nothing has been taken. That gives us an easy initial case to begin with. So then the first element comes and we can say, okay, Do the needful. This step is easy. Do exactly what you did in the previous case. Take the element wherever you can. Now when the next element comes, we actually wanted to go to row 2. We wanted to go to row 2. Instead of row 2, we will go to row 2 modulus 2, that is row 0. 2 modulus 2 equals to 0. So whatever we did in row 2, we will now do in 2 modulus 2, row 0, and change it to that. So basically when we will see, okay, we will have 5, 5, 5, 5, 12, 12, 12. We will change it over here in this way, 5, 5, 5, 5, 12, 12, 12. Same thing going forward. When I'll go to row 3, I'll say I don't have an extra row, I don't have the third row. What I did over here, I'll do in row 3 modulus 2. So 3 modulus 2 gives me 1. So I'll go to row 1 and I'll do the same things. What exactly? Like when I'm, let's say, at this element, I will say, okay, pick up from the other row. That is one answer. And basically go back by that many elements. So pick up from the top left. And in that way, basically, we will update it. So instead of saying that this is dp I minus 1j, we can keep on optimizing this. So j going from 0 to, or sorry, from I going from 0 to n, or 1 to n. I going from 1 to n, we can keep optimizing in this way, that instead of I minus 1, we can keep it as I minus 1 modulus 2. We will update this dpij also in that way. So we'll update the I modulus 2th row. So the same thing over here also we do modulus 2. Overall here also we will do modulus 2. Sorry, in pages we will not do modulus 2, that is the given array. But in dp, yes, we will do dp I minus 1 modulus 2. So in that way we are able to reduce the dp states to only a table with 2 rows and x number of columns, or x plus 1 columns. So yeah, that is this problem. A very interesting problem and a very important problem for excelling in DP. So over here, we are not taking for each state, we are not basically saying, hey, if I take you, what is the best thing? If I don't take you, what is the best thing? We are rather coming from the top and recording for every price. These small things matter. So basically, when I say I'm basically using this answer over here, that means this is a sub problem. This thing is a sub problem. So this thing, it basically says, okay, if I take this particular C element, then what remains and how do I fill that? What remains is 4. And how do I fill that? The best way is 5. So in this way, the problem of sub-problems and substructure is basically getting solved over here. So let's look at the code. The code is simple. From here the code starts and here it ends. So we are starting from the first row and going up to the nth row. Now the row value I'm calculating using I and 1. It's similar to basically doing modulus 2. Modulus 2 and bitwise and 1 are the same thing. So bitwise and 1, if it is odd, it will give you 1, otherwise it will give you 0 for positive numbers. Now let's look at this. For negative numbers, you can look at the binary form and you can decide what's the trend there. Okay, so what we see over here is we are going from 1 to up to where we cannot take this particular element, ith element. So price I minus 1 minus 1. Up to here, you cannot take the ith element. So we are just filling up the previous rows. The previous row, that is car zor 1. Car zor 1 means for car equal to 0, car zor 1 will be 1. For car equal to 1, car zor 1 will be 0. So while we are at row 0, we are looking at row 1, copying that value here. While we are at row 1, we are copying the value from row 0. Why? Because we are alternating between these steps. We are going from 0 to 1, then to 0, then to 1, then to 0, then to 1. Wherever we finish, that is our answer. So we are taking the value from card 01, that row. And over here, we are then going from price I minus 1 up to x. And we will say that, hey, from the other row you get this thing, that is without taking this element. And if you take this element, then you get pages I minus 1 due to this element. And with the remaining capacity, that is j minus price I minus 1, you already have calculated this. So take that value, dp cars or 1, j minus price I minus 1. Finally, you display dp n modulus 2 or n zor 1. You can do that way also. No, n and 1, sorry. N modulus 2 or n and 1. So dp n modulus 2x. So whichever is the last thing that you have handled, I equals to n is the last thing you have handled. So whichever row you touched, that row you should read. Right. So if you see which is our answer finally, at the end we have the answer present. This is our answer. So that's the same thing we are doing in the code. We are printing the largest, the last thing. So yeah, I hope you got some idea. We will do more knapsack problems in the coming session. Very important problem. Please practice this yourself. Let me know how you felt about these sessions. And take your time to code these things down yourselves. Then meet you in the upcoming contests and hope to see you gaining proficiency in competitive programming. Till then, take care, keep coding, and see you in all my upcoming videos.